since almost all electrical equipment, will contain some sort of embedded system, like those definitions, there's great opportunities for engineers to make a lot of money and continue making products that will include those. And a more concentrated example of those embedded system is what follows.
So pretty much I will talk about what are the common examples and how they work. So most common example is DSP chip, which is digital signal processing chip, and how it works and is related to our course is, let's say you are having a signal X of t, which is a real-time domain signal, and you will be conditioning this signal with kind of a signal conditioner, which is generally a filter. So you just get, let's say you want to get a band pass filter or a band stop filter or high pass or low pass. So it will give the signal to it. Then it will go to sample and hold. So where it converted into bits and it holds the data. So let's say from X of t, the transition to sample and hold will be n of capital T, which is n is the number of bits and t is the time period from after which it will keep repeating itself. Then from there it will go to AC to DC converter, which is pretty much a part of sample and hold. And from AC to DC converter, you will definitely get the n bits. And it will go to CPU, which will do all the computation and tell the sample and hold that it is done and get a new signal, which will again convert it and do the computation. And at the end, you will have to convert it back, your AND bits, so that's why I have a arrow going back into AC to DC converter, which will convert DC to AC, and you will get your result. So pretty much in the bottom diagram, you are having a signal, let's say you are having an input from mic or a CD or line, and the DSP chip is in the middle, which will do all this processing, the rate is defined above, and then it will again deliver to analog converter, and you will get your output. The second common example are microcontrollers. They are very powerful, low power consumption, and they are generally applied pretty much everywhere. Mostly like in automotive industries and in office machine appliances, some toys, they use it. And you are having a CPU which do all the computation, and you have serial port as he should display the picture, I/O and RAM and everything in detail. So I have a much better detail about it later on in the slide. This is EZ430 by Texas Instrument, and some of you might know it is a microcontroller which looks like a watch, and if you have a chance, just look at it. You can program it any way you like, and you can control your television, your blinds, or your lock with your hand movement. So let's say if you have a hand movement saying this, and it will raise the volume of your TV, or lock your home lock or whatever it can do. So you can pretty much program anywhere, and the programming is very, very easy. It's not like in C or Java where you have to come up with the algorithms. You have pretty much a GUI system in there, so you can drag and drop boxes and things. So that's it. And there are so many things associated with embedded systems, especially debugging, and there are so many types of debugging. I will just talk about one, which is JTAG, but commonly JTAG, ISP, ICSP, BDM poles, there are different types of it. So what JTAG is Joint Task Action Group, and they are related more on the hardware side. So let's say a JTAG team, what pretty much they do, they check the shorted connections on a PC board, whether the board is working correctly or not. What they do, they write a code with the help of design engineer, and it passes the current of some amount to all the connection and measure the voltage at each node. So with the JTAG team, you can also program FPGAs, which is kind of a chip. It is a chip, actually it's a chip, but you can use it, you can make it, program it and use it as a microprocessor as well. The highest work you can, available from an FPGA you can draw is a processor, work of processor. So you can pretty much program it, but mostly JTAG teams doesn't do it. It's a design engineer job, but they can easily do it. So, and circuit emulators like DSP use it, MATLAB and Simulink, and Allegro, Cadence, LTSpice, reliability. This is also a department, reliability department, and actually I have a quote of Mr. John, where I used to work with him in the reliability department, and he used to say, like, if a product won't break down after the period of warranty, the department will be replaced, which means like they program or they do something, or so your product will be valid for 5 years, and after 5 years you must buy something new. So what they do mostly in the reliability department, the two major tasks that I know about it are watchdog timers will reset the computer unless notified by by a software. So they will, it's like I think we have done a similar lab in ECE 265 where we reset our system. If some of you have taken it, so our traffic light where you have to reset it. It's because for a continuous long period of time you will get some sort of errors in there. So that's why you have to reset it. And for that you have a subsystem which will be shifted over for a little period of time, and it will switch back to the main system. Yeah, this is from microcontroller to microprocessor. There was a team working in University of Michigan. They were trying to come up with a microcontroller in their project, but at the end they ended up a microprocessor. So this is a one Neumann model, which is pretty much same thing for all the computers. And how does it work? You get the input and it goes into the memory. So from memory, you are having two registers, memory address register and memory data register. So from memory, it will, in memory address register, you will have the memory location of the, let's say, whatever your input is. And in memory data register, you will have the contents of that memory location. It will send it to the central processing unit, which will later fetch and process all the information and send it back to memory, from where you get the output. A more detailed picture is right here, which is instruction set architecture of a general purpose computer. So the first thing, it goes to a program counter, and the program counter send it to the MAR, which is memory address register. At the same time, it will increment the PC. So you will switch on to the next instruction. From from memory address register, the contents of memory goes to MDR, and from MDR it goes to IR, which is instruction register, and IR decode them. So let's say you are having an opcode or something, let's say you are having an add instruction. So it will decode it, the first few bits, the way it's organized, let's say you are having a opcode of add 0001, so it recognizes the first 15 to 12 bits are 0001. So it will process the add instruction, and at the end it will send it. It will go back to the fetch of the next instruction and everything. So you are having a flowchart diagram at the left-hand side, and the right-hand side is like a ISA structure. This is a picture I found, and I found it interesting because how does a computer get an input and the output? So on the top of this picture, where this picture ends, you see 16 bits are coming in. On the top of that, you are having a PC bus, which is having all the data. So from PC bus, let's say you press an A key. How does a computer know it's an A? So it goes to memory address register. Memory address register, you are having all these buses coming in. So it goes to keyboard. There's the keys coming in from keyboard data. The keyboard data register, from keyboard data register, and you are having keyboard store register. Then you have display data register and display store register. So what they do, display data register will hold the data, what you need to display on it, and get the data, and it will also give it to the display store register, which will later display. And you will see this mux. So you will select what kind of instruction you are processing. Let's say you want to process from KBDR or KBSR, and you will finally do your computation. So on the top of this, you attach this picture, which is a CPU, central processing unit,